All right, hey, so in this one, we are going to go over, as I've been labeled, my favorite problem of this unit. So this is a problem of a person bungee jumping and finding what is their acceleration at the bottom of the jump. So it says you jump off a platform of 134 meters above the river. After you have free fallen for the first 40 meters, the bungee cord attached to your ankles starts to stretch. The unstretched length of the cord is that 40 meters. You continue to descend another 80 meters before coming to a rest. Assuming that your mass is 100 kilograms and the cord follows Hooke's law, and the cord has negligible mass, what is your acceleration when you're momentarily at your lowest point in the jump? So the thing with this problem is there's a lot of different parts that are going on. We're going to have to kind of draw some diagrams. We're going to have to kind of see how we can piece everything together to get to our final answer. So the first thing I like to do for this problem is to just kind of get some heights going out to the side. Now, because we are falling, I do kind of like to say it's 134 to the bottom. So we're starting at the top. It's going to take us 134 meters to get to the bottom. The first piece it gives us is that we fall 40 meters. I just kind of like to sketch that all the way across. So we're going to fall 40 meters. This is where the kind of spring aspect of the cord is going to kick into place. It wasn't acting like a spring. We didn't really even know we had a cord until we hit this 40. It's now fully stretched. It's going to act like a spring as we go further. It says after that we go another 80 meters. Well, 40 plus 80 gives me 120 meters. So this distance in here is that extra 80 meters. So these are the different kind of spots on our graph. Those are not perfectly parallel lines, but that is okay. So we're going to consider this as we kind of start to put our different places. I guess I could have sketched one at the very top as well. We're going to have the top. We're going to have when the spring is at equilibrium, and we're going to have the bottom. These are the three different parts of this problem that we're going to be looking at. We come back up here, what it's asking for is the acceleration at the bottom. Well, we know that in order to find the acceleration, we need to know what's going on with the forces, because this obviously isn't a pure kinematics problem. So if I think about it at the bottom, we're just going to draw the person as a box like we always do. The forces acting on the person at the very bottom is gravity and the spring, so kx. Once again, as a reminder that negative in the Hooke's law just means it's opposing the direction that you've been displaced. So we're being displaced down. So the spring is saying go back up. So I'm not going to put the negative here because the negative is just saying what direction it's going in. If I do a sum of force equations for this, I'm going to have the sum of forces. That's a terrible sum. Let's try that again. Well, okay, so here I'm trying to solve for acceleration. Oh, that's way too big. We're trying to solve for acceleration. In the problem, we were given mass. We know that gravity is a constant. So that means somehow in the problem, we have to figure out what our k and what our x are. This is what we're actually trying to find from the problem. Well, I don't have any other information that I can use here dealing with forces, and so I have to think of another way to do this. Well, anytime we're talking about different parts in a track, and notice the only forces here are gravity and spring forces. That means both of these are internal conservative forces, which means if we go back to that other equation from work, the non-conservative force comes out because we're not dealing with friction, we're not dealing with drag. There isn't an external force, and so that means that our change in Emec has to be equal to 0. So that means that at each of these places, at the top of my path, in the middle of the path, at the bottom of my path, my E mechanical has to be the same. So that means the sum of your kinetic and potentials in all these places have to be the same. So we need to come over here and we need to try and figure out, do we have enough information in that to figure out what is our x? Remember, the x is our distance, between our equilibrium point and the bottom. And here, just looking really quickly, I'm like, oh, hey, let me make sure I'm using the right color here. X, wow. X is just 80. So simply by interpreting the problem and drawing my diagram out, I can immediately see that X is going to be 80. So we can come over here and actually say in our problem, it's really hard when you have to keep switching sizes on us. All right, there we go. We can actually say that we know X, which means that we really just need energy to solve for K. So that is our big goal here, is saying how can we solve for K? So now we need to look at the energy at each of these places. We're going to change colors to do that. So at the top, well, first off, even before we do this, let's make note of what type of energies we're going to see. Obviously, there's gravity, so we're going to have potential gravity. There's a spring in here somewhere, so we're going to have the potential of the spring. And because we are moving, there's going to be kinetic. So we have both types of potential energies and kinetic creating our E total or E mechanical total. And so this is, as we look at each of the different parts, this is what we're going to be looking for. So at the top, well, we haven't started falling yet, or we're just that moment where we do start falling. So our kinetic energy is actually going to be 0. My bungee cord has not started to act like a spring yet, so it is also going to be 0. And now we have to figure out my U, G. Now this is where most people are probably going to mess it up. Most people are either going to say that it's 0, which technically you could do and solve it that way, but then you end up with some negatives later on that don't make the most amount of sense. If you're okay with doing that, you're good to go. But the biggest mistake is that most people are going to want to try and say that the height is 134 because we're 134 away from the ground. But I never, or the bungee jumper, never enters this portion of the air. So they go from the top, that's 134 up, down to this was 124 away. As a reminder, when we're talking about potential energies, we're really talking about changes. That's what's most important. So what matters is the distance from the top to the bottom. That is what I'm looking for. And we did the calculations because it's 40 from the top to where the spring kicks in, and then it's another 80 to the bottom. That's actually 120. So when I'm going to come in here, when I'm going to do my MGH, I'm going to say 120 mg. The total is always really useful because when we start doing conservation statements, we're going to set the totals equal. So luckily, K and US are 0. So this is just 120 mg. That's not milligrams. That is mass times gravity. So that's E at the top. Then we're going to say E at equilibrium. Once again, I'm calling it at equilibrium because the spring is at equilibrium here. The K here is going to be, we are moving, so there's going to be 1/2 mv of equilibrium squared. Unfortunately, I don't know this velocity, so that's going to kind of throw a wrench into things. But let's go ahead and keep going. The spring hasn't kicked in yet. We're at that moment of equilibrium, so its energy is still going to be 0. And then UG, once again, this is talking about the change. We've gone 40 meters down. So we started 100, we've descended 40, so 120 minus 40 is going to give me 80. That means that we can go ahead and say here that the total is going to be 1/2 mve squared plus 80 mg. The last one we can do is come down here to the bottom. Well, here, this is the time where the spring has actually been extended. So the spring started at its equilibrium point, and it has been extended all the way out. So here, we're going to say that the spring energy is actually that 1/2 kx squared. So that's our equation for the potential energy of a spring. So it's actually extending out. It wants to pull the bungee jumper back up to that equilibrium point. So it has this potential energy of 1/2 kx squared. Now, based on the fact that we said we started 120 meters high for our jumper, we've now gone those full 120 meters. So what we really did at the beginning is we said this was y equals 0. So we now have no potential energy when we're looking at this system. If you're just isolating the jumper themselves and the jumper in the Earth system, obviously there would be some potential there. But here, when we're looking about this change, that's what's important. So we made our 0 for potential energy right here, this bottom point. And then the kinetic energy. This one really trips people up because he's been falling. We have to think like, oh, there's going to be some kinetic energy here. But notice the problem says that we're momentarily coming to rest at the bottom. The spring's been trying to pull us back up. And so we're actually momentarily at rest here, which means we have no kinetic energy. So we can say our total is simply then 1/2 kx squared. So because we have this equation over here, we know that the change in mechanical energy has to be equal to 0. So that means each of these have to be the same. So we could go to the side and set them all equal to each other. We can say 120 mg is equal to 1/2 mve squared plus 80 mg, which is equal to 1/2 kx squared. Now, it is important to ask ourselves, wait, why are we even doing this? Well, we're doing this because we are trying to solve for k so that we can solve this out and find our a. So I need to look at this and say, is there an easy way to solve for k? Well, let's highlight the things that we know. Mass was given in the problem, so we know mass. We know gravity, so we're good there. We said we know mass, we know mass, we know gravity. Okay. Obviously, the numbers are things we know. We figured out x earlier. We know that x at the bottom is equal to 80. We do not know this. So therefore, when we're trying to solve, this is not actually going to be useful for us because it has an unknown quantity in it. But I can look at this outside then and just say, okay, 120 m, we said was 100, times g, 9.81 approximately, is equal to 1/2 k 80 squared. Well, now, the only variable we're trying to solve for is k, and that's the only unknown variable. So we do some math out here, and we get that k is equal to 36.8 Newton over meters. I think I did those units right. The big thing says 36.8 at this point. And so we were able to go ahead and find this out. You need to take the time to pause the video or after we're done to go back and recalculate this to make sure you get the same number. Please feel free to do so. So now that we all feel confident in our k value, once again, we got the k value from being able to interpret this entire problem, get it set up, and then looking at the mechanical energy at the 3 different parts. The middle one really actually wasn't that useful. Knowing this 40 meters, the only reason it was useful was to recognize that that was our equilibrium point. So recognizing that the spring energy was only acting between these 2 dotted lines. And so really just kind of thinking about the differences there. Now that we have k, we can come back over here and we can actually finish solving our problem. So kx minus mg equals ma. We're solving for a, so we can go ahead and just say a equals kx minus mg over m. So we're going to end up with a equals 36.8. Once again, that x was at 80 minus 100, 9.81 over 100. And when you do this, you get a is equal to 19.6 meters per second squared. Hopefully that number is kind of familiar to you. Some places when you see this solved, it will say a equals 2g. Because this number right here is actually 2g. We could have solved this out in more variable form to get to this same final answer. But there you have it. So I recommend taking the time once again to kind of read through this problem. Make sure you feel very comfortable with how I got this set up. And then the biggest ideas here, once again, was knowing that because we're doing acceleration, I was looking at forces, I needed my K. The only way that I could figure out to get my K, the other place that I see that showing up is in energy. So I said, how can I tackle this problem as an energy problem? When we did that, we knew that at each of the portions of the jump, our energies had to be equal to each other, our mechanical energies. And so finding those mechanical energies at each of them, setting them equal to each other, and then being able to use that to solve.